Well, thank you. Thank you for the opportunity to speak. Am I a preCICE user? I would say our code uses preCICE, but David did all the work. So yeah, am I preCICE? We are definitely using preCICE, and we will definitely use preCICE more. So I want to introduce the code we're doing and the coupling things we were always doing. Here's a couple of examples. So this is a granular flow against a flexible wall. So here you've got grains hitting a wall, which is in the FEM code, and the wall deflects. This is a big problem in geophysics. And this is my favorite topic, where I was talking to the guy about the micromanagers. But here you've got a particle code, and then you want to speed it up by replacing the particles with a effective continuum model elsewhere. So these are the sort of coupling problems we're interested in. I love this slide. I stole this slide a long time ago. David saw me use this slide, 3 or 4 years ago, I think. So I was very happy one day to see this on the preCICE website, and I was reading up on preCICE, and I found this slide, and it made me very happy. So yes, I am from MercuryDPM, this is the code I started, which has been on the preCICE website for a long time in grey. I do believe it now should be black, and the XDEM has become lights, but beyond that, the plan is still there. So there was always a plan for preCICE to get particle coupling, and we were always trying to develop a code which was a particle code which could talk continuum. From conception, that was the plan. So before I get into it, I want to explain what a granular material is. It's not, I know, how many people work in grains here? More than I expected, a full 3. So granular materials are anything which is in a discrete matter form. So we're talking solid objects, but made up of discrete individual particles, okay? This is the hardest material in the world to simulate, I'm going to claim. If you don't believe me, there was a New York Times article about 8 years ago which made the same point. So it's really nasty material. So here's got some examples in industry. So this is ore extraction. Anybody know what this is? This was one of the first industrial projects I ever did. This is a vending machine serving Coca-Cola. So when you go in and push 52 and you expect cocoa in your drink, I won't talk about this problem, but they had a problem with it no longer serving cocoa. They changed the cocoa recipe and the machine no longer worked. So yeah, huge problem. This is a blast furnace. This actually happens, I'm not joking. These silos are, in granular materials, silos are engineered to 7 standard deviations of the expected stress. They still fall down. That's how badly understood these materials are. Silos still collapse. This is the most heavily used picture because somebody got it on camera. But there's about 3 or 4 silo collapses a year. And globally, about 20 people a year die trying to unjam a silo. Half of those are in America, but yeah. So silos sometimes jam, the material doesn't come out, so the guy sends somebody in with a crowbar, and then, yes. But it does happen in both ways, both that way, and it comes on the head, and that way, and all of a sudden, what feels like a solid material suddenly feels like a liquid. So people do die in these things. So they're very poorly understood. And it's not just industry, there's geology has lots of grains, some avalanches, pyroclastic flows. They're everywhere. Well, one of the statistics you probably don't realize is 78% of industrial processes use a granular material somewhere. Yeah, if you look at the research, it's tiny compared to fluid mechanics. So now I hope by the end of this meeting, half of you would decide to change topic. And anyway, okay, right. To explain what we do, because it's a bit different, we're not doing continuum mechanics, we're simulating the particles, okay? So we solve Newton's laws for particles, and then these particles have some fictitious springs and dashpots between them when they collide. So when we put things in. So what we're doing is directly simulating the grains. They might not be spheres, but complicated shapes, and we prescribe forces of some degree when they hit each other. So the way I word it, we're solving a gigantic system of 100,000, maybe 1 million coupled ODEs, but to be really nasty, these are highly discontinuous ODEs because they go from 0 to something very quickly. So it's a horrendous system of ODEs is what we're solving. Okay, so we developed a code for this. Now, contrary to what David was telling me, I would claim it's fast. He was showing me a paper from his bachelor students which said our performance was low. I will explain why there's a discrepancy here. So our code is heavily optimized for wide particle size distributions. So compared to lights, which is the code you use, we're about 5 times slower for monodisperse. We're 50 times faster for a polydispersity of 10. And then once you go even bigger, this distance just gets bigger. So our code is optimized for dealing with wide size distributions, which means it's not very quick at monodisperse. But if you're doing real problems, the world is polydispersed. I would say it's flexible because we can implement really weird stuff in it. It's got a very flexible base. One of the first things we ever did for Nestle was they were using a code I won't name called lights, And they were having problems with rotating walls because light uses triangles, and in the corner of triangles they were getting artificially high forces, whereas in our code we implemented a system where you could actually use curves, actually generate curve files or step file readers, and that was actually implemented for a company. Coarse-graining, which is different to what you were calling coarse-graining, which is a confusion in our field, and unfortunately I've infected this community with this very bad language. Coarse-graining is a technique I will say more about, but coarse-graining is a technique we spent a lot of time developing, which is a nice way to go from a particle description to a continuum level description, which we always wanted for coupling. Because the original goal was to develop two codes, a particle code and a continuum solver, a GG continuum solver, and couple the two together. One time forward, we got rid of the continuum solver and replaced it with UNFLIB, and now we want to replace it with preCICE. And yeah, but another thing is, our code is coupled with UNFLIB, which was our original continuum solver, now with preCICE, a library called Clump, which helps us do complex particles. Also with PyMore, so we can do model order reduction from within the code to get reduced order models and replace them. And this is a calibration tool which helps you learn the parameters for real materials. So granular. And so we are coupled, but we also notice what keep building interfaces for each of these codes might be a bad idea. So we'll build one interface for preCICE and put all these codes in preCICE is our new plan. So yeah. I put this slide in for Philip, but he's already gone, for Philip Newman. Our contact detection is fast. So I'm trying to prove as you go to different sizes. As you can see, our code speeds up relative to the way other codes do it by a factor of 500. So even though when we're at monodispersed, we're slower. Once we're at huge size ratios, we're bigger. And the way we did it is most codes use a link cell algorithm to look for particles in neighboring cells. We have a hierarchical of link cells. And this algorithm works really nicely. Philip, who was here early in the week, got interested in this for his autopass code, if those who know autopass. Just one quick example about complex geometries. So again, this is a, anybody know? This is a, this is a farmer mixer. So cows don't like hay, but farmers feed them hay. So to make a cow eat hay, you have to put 5% grass in it. And if you don't mix it well, they will pick the grass out the hay. So this is a mixer on a farm to mix grass into hay. And if you did it with an STL file, it's 1,456 triangles and not very accurate. Because we can natively read curved walls, it's only 5 walls in our code. So A, it's faster, B, it's more accurate. So it's a win-win situation. So yeah, so that's just showing what we can do with the complex walls. Right, the coarse-graining tool, which I'll explain a bit more. So as I always say to people, it's nice to see where 100,000 or 1 million particles went, but what did you learn? You know, do you really care? What you really care about is the continuum fields. So from its construction, we were always worried about how do we get something which speaks continuum mechanics out of particle level code. So we spent a lot of time on this problem, and I want to talk more. So this is a raw particle simulation. This is the, I think it's the velocity field, but this is the coarse-grained velocity field out of it. And then from this, we extracted data and then ran, actually this is a shower water model, somebody was speaking about shower water models earlier. This is a shower water model, and then we can directly compare. So we can show what, we can go from this particle simulation to an equivalent shower water model very quickly. This took, I don't know, a month, this takes 10 seconds. So this was always our idea. Can we speed continuum and speed it up was our original problem. And there's even an experiment here to prove it. Okay, so how does coarse-graining work? What I call coarse-graining, which is, there's two names, for this community it's fine, there's no confusion here, because you don't know the other coarse-graining. So what you do is you take all the particles as if they're point particles, point matters, and then you replace the delta function, so you define a density by saying every particle, and then you smear these properties out. You spread them with some function, and critically this function has a width W in, which is very important. You can't just freely pick it. There's a minimum and a maximum. I took the slide out how you pick this, but there's a well-defined minimum and maximum you can take for W. It's not arbitrary. The shape matters less, but the value of W really matters. So when you take these definitions of density, you stick it in your continuum equation. You literally stick it in your continuum equation, and you get back a definition of momentum. And the nice thing about this, it doesn't matter what I do. If I have one particle, one time step, or a million particles, a million time steps, the fields I get back, if I substitute them into the mass balance, they give 0. Now, the older techniques for extracting continuum information didn't do that. They gave you approximate fields which didn't have the conservation properties, and we really wanted this. Really simple for mass. If you start doing it for momentum, the formulas get really a bit more nasty and start including integrals along lines and things. But for mass, it's really easy. For momentum, it starts to get trickier. Then we spent a lot of time doing it for angular momentum external flows. When you've got segregating flows with two things, how to deal with boundary conditions and keep it conservative. We did a lot extra, which is summarized here. So we extended it for boundaries, mixtures, time evolving flow, non-spherical particles and things like that. So yeah, the basic one's really easy. The extension is really hard. So we have this nice tool. And the other nice thing about this tool, which is critical here, is there's no grid. You get the continuum equation everywhere. It might be an integral you have to evaluate, but you can evaluate that integral everywhere. So you can actually get data at the continuum level, which is finer than your particle size. So we actually used it to see boundary effects which were smaller than the particle radius, but truly there, and they were found to be there. So whereas other averaging tools require you to average over a box, and that box has to be at least the size of particles, etc., etc. This one doesn't. So, and I think, yeah, this is what David's using in preCICE. So, okay, coupling for us. How am I doing for time? Yeah, 10 minutes in, that's perfect. Coupling for us, there's 3 different types of coupling we do. Yeah. We spent a long time on the terminology, and I'm not sure we have it right. There's what we call surface coupling. So you've got grains somewhere, continuum somewhere else. So think of particles going into a bag or interacting with an obstacle. There's what we call scale coupling, where we've got grains here, and we're replacing it with a simplified lower order FEM model to speed the code up. That's what we call scale coupling. And then we've got particle fluid coupling, which is where you're solving the continuum equations everywhere, the particle equations everywhere. So we distinguish, this is our internal naming to distinguish those 3 types. But when we say fluid, we don't mean fluid, we just mean a case where there's, the continuum field is occupying the same space as the particle field. We probably need a better case. As I say, we started with ON-DEM, we are now using preCICE. So I have one overview slide of all the coupling that works with ON-DEM, which is slightly more than preCICE at the moment, but we've been using it longer. So I'm not showing any of these because I haven't got the time. This is grains in a sandbag. This is actually a really hard problem, actually. How many people have ever used a powdered soup or any powdered device in their kitchen? Yeah. Putting those powders inside the packet is way more tricky than you think. Because when you come to close the packet, if you're not careful in the design of the packet, you close packet, powder goes out. So designing packets which actually crumple around the powder rather than pushing the powder out is tricky. So we do this. So we have an FEM code solving the packet which is being squeezed around the grains and see if the grains get squeezed or pop up. Gets even more interesting with more exotic materials. You think of any food product you've ever eaten which has been wrapped. Wrapping that thing can be hard. Think of something with nuts in it which might pierce the wrapping. No hints. Okay, so we do that. We do particle fluid coupling. I was asked about multiphysics coupling, but different one. Just to prove we can do multiphysics coupling, this is thermal structural particles. So this is a beam which is thermoelastic, so it expands on the heat, and hot particles go down it. So the beam starts to deflect not only because of the stress, but also because of the temperature. The fluid structure particle fluid structure particles, we don't have an example, but we can do multiphysics. And then this is the volume coupling, where you've got a laser melting particles, but further away, you're just solving the heat diffusion equation, because a long way from the laser, it's hard. Okay, this was Mitchell's PhD, who I think, David, did you meet Mitchell? You did meet Mitchell. Yeah, okay. But yeah, he came to this workshop. Yes, the 4th workshop, he was here. Aha, thank you. So Mitchell's PhD was to develop a coupled method for what we call semi-resolved, multi-resolved flows. So there's 2 methods in fluid mechanics. You either put the particles inside the grid, or you make the fluid grid use the particles as boundaries. One works well if you've got big particles, one works well if you've got small particles. If you've got polydispersed particles, which is what our code was designed for, neither works. So this was Mitchell's PhD. Just to show, this is a very old video of mine. This is ON-DEM mercury coupling with particles in it. I call it my smelly face one, in a rotating drum with 16 particles fully resolved. Yeah, sorry, that's a really old simulation. And there's my mesh refinement. That's a really old simulation of mine. So we do fully resolved as well. And that's the first thing we did. How we do it, just one slide for the people who care. This is the under-resolved now, the under-resolved. We have coupling forces, drag forces between them. We're solving the Anderson and Jackson side equations on the fluid side. So that's the Navier-Stokes with a porosity appeared in. There's another subtle difference I'm not going to emphasize unless you're really into this. The stress isn't the stress you normally take. There's a correction to the stress, but anyway, it's a subtle point in that, which I'm not going to emphasize. So you solve these and you couple these forces. And what we're doing differently is we're going to couple, not directly, but coarse grain everything. So we're going to smear everything, which solves a lot of issues. This is with ON-DEM. What I find interesting about this, but I have got a week to talk to David properly about this, is ON-DEM works slightly differently for its multiphysics. So if you're solving thermal and fluid equations, you solve them on two grids on top of each other. And then they have mappings, which if you have to evaluate a property of the other one, it looks up which cell it's in automatically. And what we did was make a particle grid from the coarse graining. So ON-DEM had a particle mesh, which it wasn't knowing where the data came from because it was coming from the MercuryCG tool. And this was very slow. So actually what we had to do was reinterpolate so this is the particle solver, which gave back a grid of porosity and velocity. And then the fluid solver was coupled with that, but it was very slow. So in the end, we have to interpolate the particle velocities onto the fluid grid first, which is what preCICE does anyway, I think. And then it sped up the code tremendously. So anyway, I can give a variation of this. I had some 3D examples, but I don't know, I didn't bring them. So this is a lid-driven cavity for the fluid and some particles in it, so you can see the particles get dragged up. And this is the porosity field, the actual particle positions, the porosity field the fluid solver sees. And as you can see, this is a coarse-grained continuous porosity field. So the fluid solver doesn't see the particles, it gets back a coarse-grained velocity and porosity field. So this doesn't actually matter. And I think you can see some of the particles end up being bigger than fluid grid size, but it doesn't matter because it's just become a continuum field for them. So this can deal with arbitrary sized particles, which, yeah, it just works by the by without having to worry about grid refinement, he claims. Right, how am I doing for time? Yes, good. Okay, so that's what was developed in ON-DEM. So claim, you need to check this, what in 2D, using the coarse graining tool with this, A, it solved the problem of being able to go to wider size distributions because you just turn it into a continuum field and the coarse graining tool doesn't care. And B, it was 10 times faster than coding up directly the traditional coupling method between particle fluid solver in 2D and almost 1,000 times faster in 3D. But again, I think this is what preCICE does naturally anyway. But I need to get to I need to go through the details with everybody. So there's one side point, which again is based on a random conversation I had with Benjamin a while ago about commercializing and how to get paid for code. So we did set up a company in 2009. So we do have a commercial company, which does consultancy based on the code. The code is 100% open source, but we have people who consult industry using the code. And everything developed by the company also goes back in the code. And that fluid solver I just showed you was developed by somebody whose whole development time was paid for by the company. And the other big thing is we also provide access to it in already somebody was complaining about C++ interfaces, but we also provide access to it through AWS with a graphical interface. And a lot of industry partners now use it for AWS. So yeah, we also used to do consulting and training, which is one reason I came to your training course to see how you did it. We don't do it so much anymore. Yeah, since COVID, we struggled to get people to come. But, so yeah, so we did have a company. If anybody's interested in experiences and things from setting up a company, I can talk about that. Right, now the most important thing. David. So, yeah, you know this. You've been here all week. You know how preCICE works. So David came and visited us, and Mitchell started this, but David got it working, and came to couple Mercury with OpenFOAM. Okay, certain people make me very scared of OpenFOAM, often, but that was the idea. But the idea was to redo some of this coupling in preCICE. So yeah, so David came, he did it, and interestingly, we should have communicated better because David came with different test cases, but I'll come back to them in a minute. So this is a one where you've got my brain's gone. A rotating flow, and you reverse the direction, and it's not viscous, so the particles should go back exactly where they started. And this is proving the point. You may have seen this done with lights. It was published like while we were at this workshop. Lights paper. This is the Mercury equivalent, and they look exactly the same. So on the left, you've got the nearest neighbour mapping. On the right, you've got the radial basis functions. And you see what the radial basis functions work far better for actually conserving the positions of the particles and returning to where they are. But yeah, as I say, this is subtly different to what we've done in ON-DEM, so we really need to compare. But yeah. Okay, so yeah, and I think these results are, to me, the results are indistinguishable from the lights results, which, yeah, that's good. I'm just checking. I wanted it to be true. Yeah, this is the worst test case in history. Every code which ever does CFD-DM coupling in the field uses the single particle drop-in code. It's impossible to get this problem wrong. Well, if you get this problem wrong, you're in real trouble. So it's a really bad test case, because I can show you examples of codes which get this, agree in this test case. You put even 2 particles in and they diverge massively. So it's a bit of a dodgy test case, but it's one of the few with an analytical solution. And again, David's here's looking at here's the use of coarse-graining width. So looking at the effect of different coarse-graining widths and showing what, again, if you don't pick it right, you get oscillations, and otherwise you get the smooth profile. But this is using the coarse-graining. Okay, and we know that. And it's I took the slide out for time, but there is some theory about how you pick coarse-graining width. Right, the last thing I want to say, and I'm bang on time for this. So that's what I want to say about coupling and things, and how we're going to use preCICE. And the slide I took out, which probably was important now I've got a bit more time, is going forward. I've rejoined the UMFLIB team. We do plan to put the preCICE interface in UMFLIB, and then we're definitely going to compare all this through what I will call the direct UMFLIB coupling and the indirect UMFLIB coupling. And it raises a lot of interesting questions. And even you were talking to Andrew about this, and Andrew's keen to do this, is doing UMFLIB to UMFLIB coupling to preCICE, and then start asking interesting questions about that. So, because UMFLIB, the reason we picked UMFLIB is because UMFLIB is a multiphysics library, so it already has lots of fields in, and it's monolithically coupled. And at some point, and again, I talked to Benjamin about this, I was brainwashed what monolithic was always better than segregated solvers. I will be careful what I say in this room. But so it'd be nice and interesting to compare this and do this. So this is what we're going to do. So anyway, the last thing I want to talk about is the cost action, which is actually paying for me to be here. So we have this European cost action. How many people know what a cost action is? Okay, how many people don't know what a cost action is? Right, okay, so I'll say. So a cost action it stands for cooperation in science and technology. And I think you could really apply for a preCICE cost action. You just need like 7 countries to say they're interested in the action to get the money in the first place. So it doesn't pay for any work, any staff time, but it pays for meetings, workshops, training, and visits. And it pays for you to visit other people and get them, and it's open to industry and academic members. We have one on DEM to bring together the DEM community, to bring normalization and standardizations, and lots of things you've been discussing this week for the DEM community. So we have one which is designed to promote the use of open source DEM and bring it together. So I want to say a little bit more about this. Yeah, the codes. If you guys are interested in it, these are all the open source DEM codes which said they were committing to the project. There's 2 very active ones and some less active ones in this project. Also, the one non-DM code who committed to the project was PowerView. PowerView are an official member of this project. I'm hoping I can convince 2 more codes to become official members of the project. No hints. Somehow Philip got out of the room before I put this slide on. But yeah, I've been working with Philip for a long time, and I actually got one of his postdocs to join, and then 4 weeks later he took a job in industry. So, okay, so yeah, so the network has various goals. One is look at speeding up the codes with GPU deployment and multiscale stuff and machine learning. But some things you've talked about, benchmarking and normalization between codes, common data formats and things, making codes more compatible, and even promoting the use of open source in the industry. But key things for you guys is coupled problems comes under this. How do we do more complicated physics? And coupled problems comes under this. And the network is not just for DM people, it's for people who can contribute something to the DM community. And I think most people in here who do fluids and things could definitely fall into that category. At the moment, it's going to sound an odd complaint, but we're a bit DM heavy. We could do with more outside skills in there. David's a member and came to one of the meetings. And I think found it okay. Yeah, good. And we're definitely short of people with a more numerical orientated background. Lots of engineers in this network, so we could do with more people who think more like computer scientists and engineers. Okay, that's the last thing I want to say. So thank you. I think I was reading on time. I have to say, it's, I don't mind saying it, but it's also a legal requirement to put all these logos on. So the cost network actually paid for me to come to this workshop on the justification of this workshop, somebody being at this workshop is relevant to the network, and it's also paying for me to visit David next week for a week. So think about it. So if you join the network, you could get money to visit somebody to learn DEM, or you could even then put a little bit more pressure on maybe having preCICE as an official training course. And the last thing I want to say, we are writing the follow-up network because it's been very successful, and there's a much more strong influence on coupled problems in the follow-up network. So even if you don't join this one, maybe you want to pop around to be involved in the follow-up. As I say, it only pays for things like this, but then you can run courses like this for free, inverted commas. It gives you about $250,000 a year to run training courses and things for your software. So I think it might be useful. Anyway, thank you. I think it was okay with that.
Yeah, thanks a lot for this encouraging talk. There's, I guess, time for questions.
Yeah, thank you so much again for the interesting talk. I myself use CFD-DEM coupling, which is like lights and open form, and I find your approach also very interesting. Something I didn't first of all get regarding the test case that you showed, the one particle. I understand that you are mapping the porosity field from the particle solver to the fluid solver in order to resolve, let's say, the particle. So are you fully resolving the particle like presence here? Is the grid fine enough to represent the particle regarding the porosity?
I can show this better, not on David's slides, but on the other slides. You're still thinking there's a grid, that's the point. So what I'm trying to say here is because we're coarse graining, we have a coarse grain grid which can be anywhere. The coarse graining can be evaluated anyway, so it doesn't matter where the particles are. We have a porosity field we independently refine. Oh, am I explaining this well?
Yeah, but the
particles are gone. So we smear the particles to a continuous field, and then we refine that continuous field.
Yeah, but this smearing, does it take really, the size of the real size of the particle into account? Okay, yeah, I understand. But now the other question is regarding now the fluid forces in this particle.
Yeah, at the moment we only have the basic ones, yes.
Okay, are the pressure drag and viscous drag being resolved on the surface of the particle, or?
No, it's under-resolved. It's under-resolved.
Okay.
So no, that's the point. This is the fully under-resolved case. So no, the engines and injection are getting a porosity field, and then on the particles back the other way, we're just applying a simple drag law from the fluid solver. So in that sense, it's under-resolved.
Okay. Last question is, where do we find this coupled through preCICE? That's open form, Mercury. Is it already published online? Can one still?
7 days ago.
7 days ago. Yeah. Okay.
Me and David will clean up the documentation and test cases shortly. It's got good documentation and test cases. I want to make them more obvious.
Well, not in a hurry, but I mean, something is coming soon regarding that, right?
No, it's there.
Okay.
It was the last merge pull request from Mercury 7 days ago. And
okay.
Got a hard time.
I'll make sure to check that out. I'll make sure to check that out again. Thank you so much.
It's there and it works.
Thank you so much. Thank you.
Yeah.
Further questions? No, it doesn't seem to be the case. Then thanks again.